Thank you, everyone. My name is Derui, and I'm going to present our paper, Provably Unlearnable Data Examples. The authors of this paper come from CSIRO's Data 61 and the University of Chicago. Also, the project is funded and supported by Cybersecurity Cooperative Research Centre of Australia. In this talk, I will first cover the background and motivation of our work. And next, I will introduce the proposed theory on the certified learnability of data. Also, I will go through some major experiment results. And at the end of this talk, I will introduce some immediate applications of our work and also directions for further improvements. As many of you are aware, the learnability of public data can actually pose some great risks. In early days, attacker can collect data from public domain and train shadow classifiers for membership inference. Also, this data can be used to train substitute models for launching transferable adversarial attacks against other black box models. Nowadays, with advances in foundation model, especially open large language models and open large vision models, and also PEFT techniques, data exploitation has never been easier. The attacker now can collect less data, but do more harm. So for example, the attacker can collect data from social media and use them to fine-tune pre-trained models and make these models as adversarial domain experts, which can expose sensitive knowledge. In a recent MIT technology review, an artist has his paintings being used in the fine-tuning of a stable diffusion model, and this stable diffusion model will later generate images mimicking the style of the paintings, and the fine-tuning only requires 20 paintings, and obviously this damages the intellectual property of this artist. There are several laws and regulations from different nations trying to stop this action. However, unfortunately, there is no strict guarantee on the learnability of data. And to reduce the learnability of data, there has been a line of work named Unlearnable Examples. Also, we have other names for this line of work. So in these words, data points are perturbed to unlearnable examples before publication, and machine learning models trained on these unlearnable examples will demonstrate quite poor performance on clean data, which means they have a very low utility for the data from the same domain. However, there are several problems for the current research of unlearnable examples. So the first is the generalization issues caused by different and diverse pirate models and training strategies in the wild. Second, evaluating unlearnable examples is quite hard due to the stochasticity in the training process. Also, in this paper, we discover a new threat named recovery attack. And in this attack, the attacker can slightly perturb the weights of a pirate model trained on unlearnable examples. And then with a small portion of clean data and projected SGD, the performance of this model on clean data can be restored to a near normal level. And this attack might be particularly interested by attackers in federated learning setting because the attacker can upload a local client model which was attacked to poison the global model, so the global model will violate certain data privacy or data availability protocols. So all these problems suggest that unlearnable examples are very vulnerable at the moment. Motivated by these problems, we want to ask this question in our paper. given a set of unlearnable examples, can we establish an upper bound on the utility of pirate models trained on them? Obviously, this question is very hard to be thoroughly answered. And obviously, training with different models and learning algorithms for millions of times to estimate this upper bound is not practical, right? And also, there is no tool for computing this upper bound at the moment. But in this paper, we find that it is possible to derive such an upper bound with some constraint. So to this end, we introduce our proposed frameworks on the certified data learnability. There are 3 parts. In the first part, given a dataset DS to be protected, we will search for a set of perturbation delta under the help of a surrogate model. So after applying this delta to the dataset, it will minimize the training loss of the surrogate. Also, for this surrogate, we use random weight perturbation to make it more suitable for the later certification process, and also let us generate more robust, provably unlearnable examples, or PUE. In the second part, given the previously trained surrogate, we will randomize its weight using Gaussian noise. And for n times, for each randomized copy, we will evaluate its utility using some matrix A and a test dataset. So this matrix A can be any matrix, so that means our framework is quite generic and can be applied to different tasks and data modalities. Later, given all the results, we will compute a Q-eta learnability with the help of a quantile parametric smoothing function. We also display the definition of Q-eta learnability here. So the green highlighted part is the guarantee on the maximally attainable utility of pirate models. And also we have some constraint. So here we have a certified parameter set. As long as the trained pirate models with their parameters falling within this set, this guarantee will be true. Later in the third stage, if the defender has no access to this private test dataset, the defender can also sample a test set from a closed domain and use that to compute a generalization learnability score with the help of Hofstein's bound. To the best of our knowledge, this is the first certification framework towards the effectiveness and robustness of unlearnable examples. And how to certify it? So first, we will have a quantile parametric smoothing function, or QPS function. And this function takes the randomized parameter or weights of the model as input and computes the model utility at a given quantile Q among all attainable model utilities, which is the population. And also, we will have a perturbation bound on this QPS function. And this bound helps us to certify the learnability and calculate a certified parameter set, which scales with eta. We also have our certification algorithms here. Due to time limit, please check our paper for more details about the algorithms and theorem proofs. So examined some key properties of the certification. Based on certification results on different datasets, we find that using larger values of Q and eta in the certification can help us to certify higher learnability scores. Also, we introduce random weight perturbation for training better certification surrogates. By comparing the certification results from RWP surrogates and the baseline, we find that the RWP surrogate can produce higher certified learnability on the same set of unlearnable examples compared to the baseline. This means RWP can help us to create better certification surrogates. Based on the RWP surrogate, we also generate something called Provably Unlearnable examples. We compare PUE with the baseline, and we find that under the same training method, which is RWP, PUEs have lower certified learnability compared to the baseline. This means that PUEs can lead to more robust protection against certifiable adversaries. Beyond this, we also evaluated the protection power of PUEs against pirate classifiers beyond the certified parameter set. We evaluate the protection power using recovery attacks and compare PUE with another two baselines, namely EMN and OPS. We find that it is actually harder to recover models trained on PUEs than recovering models trained on the baselines. This means that PUEs can also provide more robust protection against those general adversaries outside of the certifiable parameter set. So, at the end of this talk, there are some immediate applications of our work. First, certified learnability can serve as an evaluation metric for unlearnable examples. Second, certified learnability provides a data availability guarantee before publishing the data to a public platform. Also, based on our work, we can generate robust provably unlearnable examples for better protection of the data. As for the directions for improvements, first on coverage, we can expand the certified parameter set by improving the certification algorithm. This allows us to capture more pirate models in the wild. On tightness, we can certify higher learnability by training better surrogates. And at last, on the efficiency, we can accelerate the PUE generation and surrogate training process. Thank you for your attention. Please let me know if you have any questions.
Do you have any questions from the... Okay, I'll go ahead.
Well, congratulate again on your Distinguished Paper Award, and really nice work. So I wonder if the surrogate model, the learnability of the sample will depend on the model structure or the set of other training samples, like they may be correlated. So how do you address that part?
Thank you for the question. Yes, actually, we have a set of experiments in our paper testing the impact from model architectures. And we find that generally, for the transferability of the protection, it is it can transfer between different model architectures. If we generate the perturbation based on, let's say, ResNet 18, the perturbation can still be useful for other architectures like ResNet 50 or DenseNet. And in the certification, of course, if the surrogate model gets larger, it will bring more challenges to the certification because we need more time for the process, and also we may need to have some limitations like curse of dimensionality. Yeah. Thank you.
Okay, thank you.
Thank you.
Any other questions from the audience? Okay, let's thank the speaker one more time. Thank you.
Thank you.